One place where indices can be extremely useful is when we're dealing with huge and or small numbers. To do this, we use something called scientific notation. Here's some examples of some numbers that are really large or really small. The first one, the distance to the nearest star from the Sun, Proxima Centauri, is 39.9 million kilometres. That's a long way. In fact, it takes light 4 years to get to us from there. The mass of the Earth is 5.980 million kilograms. The number of atoms in the universe is about, that is such a large number, I'm not going to even bother trying to say that one. It's a 1 with 80 zeros after it. That's one huge number. It would be very easy to muck that up and leave a zero off or put an extra 1 in when it's a huge number like that. Same with all these other numbers. The size of an atom is about 0.000000001 metres. And the smallest theoretical measurement that we can make, called the Planck length, again, that is such a small number it's too easy to muck it up by trying to say it. Thankfully, indices can save the day, and we can use something called scientific notation to help us write these numbers more accurately and with more understanding. So, scientific notation uses indices to help us write numbers like the ones that I've got on this page here. So let's have a look at how that's done. The first number I've got is 1,230. If I rewrite that like this as 1.230 by 1,000, then that's worth the same amount. Then I can rewrite it as 1.230, and instead of writing times 1,000, I'm going to write by 10 to the power 3, because 10 to the power 3 is 1,000. That number is now in scientific notation. Scientific notation has two parts: a normal number, or a normal decimal number, where the decimal point is always after the first digit, and it's multiplied by 10 to the power whatever. In this case, it's 3. Let's have a look at the next number, which is a small number. If I was going to write this number the same way, I would be writing it as 7.8 divided by 1, 2, 3, 4, 10,000. Now another way of writing that is 7.8 divided by 10 to the 4. Now we know when we divide, it's the same as multiplying by the fraction turned upside down. So 10 to the 4 over 1 could be turned into 1 over 10 to the 4. Also, we also know from indices that if 10 to the 4 is on the denominator, we can move it to the numerator by making it a negative power. So this last number here is actually the scientific notation for a small number. You'll notice that when it's a large number, bigger than 1, you end up with a positive power for the power of 10. When it's a small number, you end up with a negative power. So in scientific notation, a negative power for the 10 is a really small number. A positive number is a big number. Now the last example that I've done, I showed all the steps so you could see how we got the -4. In reality, what we do is we use a shorter way to work out what the scientific notation would be. So let's look at that. In the first question, where it's 1,230, first of all, I just need to write 1.230. So that's just taking the 1230 digits and making sure the decimal place is after the first digit. Then I multiply by 10 and count how many places I moved the decimal point to get it there. So if I look at 1, 2, 3, 0 above, 1, 2, 3 steps, so I need to put a 3. In the second question, I do the same thing. I write the short way. I write 7.8 by 10, count the number of decimal places, 1, 2, 3, 4, and write -4 because it's a small number. You can see if I count to the right, it ends up being a negative number. If I count to the left, it ends up being a positive number, which sounds a bit confusing because normally we have left is negative and right is positive. So if you're not sure, just remember big numbers like this one here have to have a positive power. Small numbers like this one here have to have a negative power. Using the same method, by counting the number of decimal places, here are the answers when you change the numbers we had originally into scientific notation. So a really large number like the distance to the nearest star from the sun ends up being written as 3.99 by 10 to the 13. The mass of the Earth ends up being written as 5.98 by 10 to the 24 because there are 24 places to move the decimal point. And the number of atoms in the universe is 1 by 10 to the 80, which because there's 80 zeros after the 1, or you could just write that as 10 to the 80 because 1 times something is the same as itself. For small numbers, such as the size of an atom, we end up with 1 by 10 to the -10 because you have to move the decimal point 10 places. You notice in this one with the 1, we didn't put the point in. It's not necessary because there's no other numbers after the 1. The Planck length ends up being 1.616 by 10 to the -35, a much easier number to remember than this long decimal version. Also, for every 0 you left out of the long decimal version, you would be making the answer 10 times bigger. If you left 2 out, that's 100 times bigger. Let's look at a couple of examples of using scientific notation when multiplying and dividing and how indices are involved. In the first question, we've got 4 by 10 to the 5 by 2 by 10 to the 6. That means if I was going to multiply those, I could write it like this: 4 times 2 by 10 to the 5 by 10 to the 6. It doesn't matter with multiplication which comes first, so I've just rewritten it so it's easy to see. 4 times 2 is 8, and if I was multiplying 10 to the 5 by 10 to the 6, I would add the powers, so 5 plus 6. So that means it's going to be 8 by 10 to the 11. In the example below that, same sort of idea. Let's rewrite it. 5 times 4 by 10 to the 12 by 10 to the -4. 5 times 4 is 20. Let's add the powers because we're multiplying the numbers. So I've got 10 to the 12 plus -4. Now when you add a negative, that's the same as subtracting. So that's the same as 20 by 10 to the 12 -4, which is 8. So 20 by 10 to the power 8. Now I can't leave it as 20 by 10 to the 8 because that's no longer in scientific notation because the 20 has got too many numbers before the decimal point. So I need to rewrite that as 2.0 by 10, because that's what 20 is, by 10 to the 8, which will equal 2.0 by 10 to the 9, because if I've got 1 plus 8, I get 9. In the last example with division, I'll just rewrite it this way: 4 by 10 to the 7. Sometimes I think if you do it this way, it helps people understand the division part of the numbers. So 4 divided by 2 is 2. 10 to the 7 divided by 10 to the 5. We subtract the powers this time, so 7 take away 5. So the answer is going to be 2 by 10 to the power 2.